And welcome to Chapter 5. So today we are going to go over Chapter 5, and we'll go over Chapter 5. Oops, I'm sorry about that. Just give me 1 second. And where is Chapter 5? Chapter 5 is right here. Let me bring it up. We're going to talk about the Ethernet protocol. And the Ethernet protocol specifically is the most widely used Ethernet physical LAN, wired LAN I should say, the wired LAN in the world. So the most widely used wired LAN in the world is Ethernet. So once you understand how Ethernet operates, you'll understand how switches work, and you'll be able to troubleshoot, maintain, and upgrade an Ethernet LAN. All right, so let's get started immediately. What is the Ethernet protocol? Ethernet operates at the bottom 2 layers of the OSI model. It can give you bandwidth up to, as you can see, over 100 gigabit per second. And as you will see later on, it is the most widely used. Even though it operates at 100 gigabits per second, most likely you will see either the 100 base is the most widely used, and some may use the gigabit Ethernet. And so in the near future, so this is Ethernet's going to be a while with us, even though, you know, like 10 gigabit, 40 gig, and even 100 gigabit, not even close to using it. So again, it's the bottom 2 layers of the OSI model. So question number 1. I always said to you, I'm going to be asking you questions. And here's question number 1. Someone asked you, at what layers of the OSI model does Ethernet operate? And the answer is the bottom 2 layers, layer 1 and layer 2, specifically the physical and the data link layer. The LOC is really in software, which is your PC takes care of that. And the MAC sublayer and the physical layer is on the NIC itself. That's on the hardware. That's where all the encapsulation of the frame, placing the frame on the wire and retrieving the frame from the wire occurs. All right, the LLC, the logical link control sublayer, as we've discussed from the last chapter, that's the one that grabs the packet from the upper layer, places it into a frame, and then on the frame itself will indicate what type of packet that is placed onto that frame. This, if you remember from last chapter, that's the example of the pizza guy that makes up the boxes and places that the pizza in the box and just writes what type of pizza he places in that box. And he gives that pizza box the unfinished frame, the labels. He gives it to the MAC sublayer. What does the MAC sublayer do? He finishes the labels that are placed on that frame and then places that frame onto the wire, sends it out. And he's also responsible for retrieving the frame. If there's an incoming frame, he's the one that takes that frame and brings it in to process it. The MAC sublayer, that is. All right. The MAC sublayer, as you can see, is made. You know, the NICs are really made up of a whole bunch of different types. There are many different flavors. There's the 10 base 5, 10 base 2, 10 base 3, and so on. Now, the naming convention for Ethernet falls into 3 parts. The first part is the number, the 10, for example, indicates the bandwidth. So if you see a 10 base T, that means that NIC has a bandwidth of 10 megabits per second. 100 means 100 megabits. A gigabit means 1,000 megabits per second. All right? So just give me 1 second, and 1 second, guys. I need to do something, and I'll be right back. Oops, no, I cannot go back. No, I can go back right here. So I'm going to pause for a minute. Okay, let's continue. Sorry about the delay. I just had to do something really quick. All right, back to where we were. So the first part, like I said, indicates the bandwidth of the NIC, how fast data is going to be transmitted. The second part, the base, the word base means baseband. It's really talking about the signaling. In this case, base means baseband, and that refers to one signal is being transmitted, one frequency. That's compared to broadband, which means multiple frequency being transmitted. Of course, you prefer broadband, but Ethernets do not do broadband. They are only baseband type of technologies. Now, the last part in the name talks about the media. So if you see the number 5 in the old coax, or number 2, 5 means 500 meters. The cable can be extended up to 500 meters or 185 meters for the 2. If you see the letter T, means you require a twisted pair cable connected to that neck. If you see anything other than T or C at the last part, it really indicates it's a fiber optic cable. The first 3 types are the legacy Ethernets, which means they are really not used. Most people use 100 base or higher. And like I said to you, the MAC sublayer is responsible for data encapsulation. That means putting some bits in the beginning of the frame to indicate that that is the beginning of the frame, finishes the addresses on the frame after it receives it from the LLC, and that it'll indicate the source MAC address. You get it from the ROM chip on the NIC. The destination MAC address, most likely you'll get it from an ARP request. And you'll also place on the frame something called the FCS, the frame check sequence. That's the error detection. So what you do is you put a number in there, so when you send that frame, this is to check the integrity of the frame. The other person on the other hand is going to double check the frame and see if they can match that number. We'll talk about that in a few minutes. So once the frame is done, data encapsulation, meaning finishing the labels that are placed on the frame, and then the MAC sublayer is the one that is responsible for placing that frame onto the wire and also retrieving that frame from the wire if there is a frame coming. Okay, so that's what we just discussed. We'll talk about the error detection in a few minutes when we take a look at the frame itself, and that is the part of the slide that we missed from chapter 4, which I'll discuss in a few minutes. All right, the MAC sublayer. He's responsible for placing the data onto the frame, onto the wire. Now, the problem is you don't just go ahead and just place the frame onto the wire. Imagine that you are driving and you coming into an entrance of the highway. You don't just keep driving. If you do that, you're just getting, there's a good chance that somebody might hit you. Same thing with the Ethernet. The Ethernet NICs, when they want to send data, what they do is they go out and they do carrier sense. They sense to see if there's traffic. They sense the segment to see if there's traffic. Now, you may not be the only one that is sensing the segment to see if there is traffic. There are multiple people at the entrance of the highway, for example. And once they all sense that there is no traffic, what do? They all jump in at the same time. That's what multiple access means. And that's what contention comes into play. They call it contention. First come, first serve. Everybody's trying to go first, right? They're contending to use the segment. Now, having done that, there's a very good chance that there's someone else got on the segment and try to transmit data with you. So what you do is you use something else called collision detection and trying to see if somebody hits you. And if somebody hits you, what you do is you back off and you'll try again to transmit again. And hopefully you'll be the first one out. Ethernet and the wireless, both of these use this technique. But the difference between Ethernet and wireless, even they both use the CSMA, but Ethernet used the collision detection, and the wireless 802.11 they would use the collision avoidance. Instead of trying to detect if somebody hits you, what the wireless 802.11 do is that they send out a signal and to say, hey, I'm trying to transmit. Is everybody okay with it? That's called collision avoidance. That's what the CA is for. Okay? So that's the difference between the CMA/CD and the CMA/CA that the 802.11 NICs use. Okay, what is the MAC address? The MAC address is the name or the number that identifies the device. the NIC. It comes into the NIC. It's a burnt 48-bit number that's embedded on a ROM chip on the NIC. And where does that 48-bit number come from? And it comes from the vendor. The vendor makes up 24 bits. It's called the serial number. And then he calls the IEEE, asks for another 24-bit number called the OUI, the Organizational Unit Identifier. And then they'll sandwich these two 24-bit numbers together, and that's how you come up with a unique 48-bit number. It means no one else in the world will have that number. Okay, so it's unique to that NIC. And it's typically written in hexadecimal number. You know, the hexadecimal numbers brings the number and writes it in a concise form in a 6-byte number instead of writing 48 bits. Okay, and we'll discuss on how to, in a few minutes, we'll take a look at how to convert binary to hex and hex to binary. And we're also, in class, we'll be discussing how to do the IPv4, you need to convert decimal to binary, binary to decimal, and so on. So we'll learn all of that in class. We'll be practicing more and more about that. But here is the frame that we did not do from chapter 4, the Ethernet frame. There are two types of Ethernet frames. There's the IEEE 802.3 and there's the Ethernet 2. The most widely used frames that is being transmitted on using for TCP/IP, it uses the Ethernet 2. So that's what really your NIC uses every time you're trying to transmit the TCP/IP protocol. The IEEE, so what actually took the Ethernet 2 frame and they tweaked it a little bit. As you can see, this label type changed it to length. The preamble, they split it into a 7-byte and a 1-byte. Let's discuss the Ethernet 2 frame. Let's go in right here. This is the data. This is the packet that comes from layer 3. So when LLC grabs the packet from the network layer and places it into the frame, that packet cannot be larger than 1500 bytes. All right? And it cannot be less than 46 bytes. Okay, so question number 2. What's the largest packet size an Ethernet frame can hold? The answer is 1500 bytes. What's the lowest size a packet an Ethernet frame can hold? 46 bytes. All right, so once the packet is placed in, then what LLC does is he stamps a 2-byte number onto the frame to indicate what type of data he just placed in here. What type, meaning is it an IP, is it an IPX, is whatever. Okay, but most likely it's an IP. That code, that 2-byte code, will indicate what type of data to send there. Then he takes that frame without doing anything else and gives it to the MAC sublayer. What does the MAC sublayer do? Grabs that 48-bit number, which is a 6-byte number, from his ROM chip and places it right here, and then does an ARP request, requesting the MAC address of the destination, and stamps it right here. And then this frame from here to here, you put that frame into a calculation called the CRC check, which is really a hash program that's going to take a look at the frame, take a snapshot, and come up with a number. And that number is placed at the end of the frame, called the frame check sequence. And the reason you do that is when you send the frame out and you receive it, the first thing that you're going to do is run the frame into the same CRC check, the same hash program. And the number that algorithm comes up is supposed to be the same number that is stamped on the frame. If it's not, that means the frame has been either tampered with or has been corrupted. So what you do is you drop it. You don't accept it. If it's the same, then the frame is good. And then you go ahead and process it. If you drop the frame, after a certain amount of time, the sender will realize that that frame is no good because he didn't receive an acknowledgement from you. He'll have to resend the frame over. The preamble is an 8-byte number, which means it's 64 bits of on and off, 0, 1, 0, 1, 0, 1. This is really to indicate the beginning of a frame. And those 64 bits are only used by the 10 base T NICs or lower, the legacy Ethernet. But nobody really looks at them. So if you have 100 base T NICs or higher, they don't even bother looking at the preamble. They'll start looking at the destination address immediately and try to compare it to see if it's for them or not. But every single Ethernet NIC, the regular Ethernet, the 10 base T, the fast Ethernet, the 100 base T, the gigabit Ethernet, the 1000 megabit T, all of those will create the frame with the preamble in it before they transmit it. All right, so looking back here, by the way, so the frame size is 4 plus 15, the maximum frame size. 4 plus 15 plus 2 plus 6 plus 6, that comes up to 1,518 bytes. So if your frame, the maximum frame size, Ethernet frame size can be is 1,518. The minimum size is 4 plus 46 plus 2 plus 6 plus 6, that comes out to 64 bytes. So there are some switches out there that will look for 64 bytes at minimum of a frame, because if you are a frame that is less than 64 bytes, that means you're no good. And therefore switches, when they recognize that there's this frame that is coming is less than 64 bytes, they drop it. They don't even allow it to go into its destination. It's considered to be a fragment. Any frame that is less than 64 bytes is really considered to be a fragment, and most switches, they are fragment free. What they do is they drop the frame and don't let it go onto its destination. Now, in some cases, when you have two switches, which we'll discuss this next semester when we're talking about VLAN, there are going to be two switches and they're going to have a trunk between them, where VLANs on one switch want to pass data to their own VLAN on the other switch. They have to use the trunks, and when they get on the trunks, they are tagged to indicate which VLAN you are coming from. And when you give that frame a tag, a 4-byte number, that's going to increase the number. It goes from 1518 to 1522. But what happens is when the frame is traveling on the trunk and just before it enters the switch says, oh, let me see the tag. Oh, you're going to VLAN 10. He removes that tag, brings the frame back to 1518, a normal size, and then he'll send it to you. So you as a receiver, you will never see the tags on the frame. Only tags, or the frames are tagged when they are traveling on the trunk between switches. We'll discuss more about this when we talk about VLANs next term. All right? So we've discussed all the fields that are on the frame, as you can see. This is the 802.3. The start of the frame delimiter is really 0, 6 ones and a 0. The 7-byte number now comes out to 56 bits of 010101. The length is a 2-byte number instead of type, which really it's to indicate how big the data is that's in here. That's what the IEEE 802.3 did when they tweaked the Ethernet 2 frame. But again, the Ethernet 2 frame is the one that is used when you are doing TCP/IP. Okay. Now, the hexadecimal numbers. We will discuss this in details, and we'll have some practice worksheets on this because we need to know how to use this. We need it for IPv6. An IPv6 is a 128-bit number. You're not going to sit down and write 128 ones and zeros. So what we do is we want to write that number in a more concise format, shorter format. And the hexadecimal helps us do that. Hexadecimal, we can write 1 byte, a 2-digit number, into 8-bit instead of writing 8 bits. So each digit in a hexadecimal number is equivalent to 4 bits. And a 4-bit number is called a nibble. So this 0 is 4 zeros, this one is 4 1. What you should really do is remember this chart right here. Decimal means there are 10 unique digits, 0 to 9. And before they start to repeat themselves. Binary means 2 digits, 0, 1, and then they start to repeat themselves. Hex means there are 16 unique digits before they start to repeat themselves. 0 to 9, and instead of writing 10, you write A, B, C, D, E, F. And then you start with, 1, 0, 1, 2, 1, 3, all the way to 1F. And you go 2, 0, and so on, right? For example, let's say you want to convert CA to binary. So you look at the letter C, it's a 4-bit number. The letter C is 110, so you write 110. The letter A is 101, so it's 101. Simple as that. If you want to write 76 in hex, so you write 0 and 1, 0, 1, 1, 0. All right? We'll discuss more of this when we do when we talk about IPv6 and when we are practicing with these worksheets in class. All right. If you are asked to find out what your MAC address is, okay, so what you do is you type ipconfig/all, and there's your MAC address right here. That's your physical address. You'll also be able to get your IPv6 address and IPv4 address, as you can see right here. All right. We'll talk about that in practice when we are practicing in class. Anyway, there are 3 different MAC addresses can be transmitted from a device to the switch to a destination. There's the unicast address. A unicast address is when you want to send a frame that is destined to only one device. If you see that this destination MAC address right here is the destination MAC address, is the same MAC address as the server, and its IP address, the destination IP is this guy right here, only the server IP address. And the source IP and the source MAC is the same as each one. So this is a unicast, meaning it's only going to be sent to one device. A broadcast is when you place FFFFFFF on the frame. This is a typical broadcast address is when you do an ARP request, which means you want to send a frame to everybody in the LAN. So when a switch receives a frame with all ones in it, he sends it to everybody. And the IP address, as you can see at the end, is all 11. We'll talk about that when we're doing subnetting 255. A multicast address is an address is when you want to send a frame to multiple users, not everybody in the LAN. And that what you do is you give these 3 guys an address that starts with 224, class D address, if you are familiar with IPv4 classes. And the MAC, your destination MAC address should start with 0010058, and the last 24 bits is really your IP address converted into hex. And when you transmit that frame, it goes only to the people that have the 224 IP address. We really don't do a lot of multicasting, although we'll discuss that in IPv6, because IPv6 doesn't use multicasting. Doesn't use broadcast. It uses only multicast. So what they do is it's really called multicast. They don't call it broadcast, but it does the same exact thing. But multicast as a practice, for example, IPTV uses multicasting. As an example, let's say in your neighbor, you and several of your neighbors subscribe to HBO. So what HBO does is they give you an IP address, for example, that starts with 224, and when they send out the HBO signal, they send it on that 224.00200, and you have that address. If you have that address, you'll get the HBO. If you don't have that address, you're not going to get it. That's what it really comes down to. All right, again, we're not going to talk about multicasting. I think it's beyond the scope of this course. All right, now you should know the difference between a MAC and an IP address. So if somebody asks you on an interview, what is the difference between the MAC and an IP? Well, this is question number 3. What do you say? You say that the IP identifies the location of the user, the LAN, and it's similar to a zip code. And it's used by routers to pass a packet from one router to another. And remember, routers act like post offices, and the post offices look at zip codes. Routers look at IP addresses to find out which location you belong to. The MAC address, on the other hand, identifies the person, the host inside that zip code, inside that LAN. So when you communicate with other devices inside your LAN, you use your MAC address, you use your physical name, and the physical name is placed onto the frames, and frames are passed from one device to another device inside the LAN, right? So you need both of them. Okay. Here's a typical end-to-end connectivity. Your MAC address and your destination MAC address, and here's your source IP and the destination IP. The IP addresses are on the packet. The MAC addresses are placed onto the frame. Okay, as we've discussed from last chapter, the packet will travel in different frames. So here we're doing Ethernet frame, then the packet leaves and gets into a fiber optic frame, and then the packet leaves, gets into an 802.11 frame, wireless, well, maybe not 802.11. And then it's still going wireless, then gets back on a fiber optic frame, and then here's the 802.11 frame probably, right? So remember, that's very important to understand. Packets will be transported into different frames as they traverse the network till they get to their destination. All right, let's talk about ARP. I know we've discussed it in chapter 4, but let's repeat that because it's very, very important to understand. Well, I don't know if we discussed it or not, but either way, here's how it works. Let's say you want to send data to somebody in here. Here it says, I need to send information to the .7 to this guy. H1 wants to communicate with H4. He got his IP address. He stamped it on the packet. He has his source IP address. But now he places that packet into a frame, and then he puts his MAC address onto the H1 MAC address on the frame. Now he needs the MAC address of H4. He doesn't know it. So what does he do? He sends out an ARP request. He'll say, hey, whoever has the IP address 192.168.1.7, please give me your MAC. I have a packet I want to give you. So when I send that broadcast message to everybody and when the switch receives that broadcast frame, he sends it to everybody. So H4 will hear that and he'll see his IP address and he will send what's called an ARP reply back to H1. And H1 will take his MAC address, stamp it on the frame, and sends it to him. So to make sure that he doesn't have to keep doing ARP requests and keep asking him, he'll take his MAC address and puts it in memory in an area called the ARP cache. So if he needs to communicate with H4 again, he'll just grab that MAC address from his memory, places it, and sends it out. He doesn't have to do. You only do it the first time if you don't know his MAC address. And the cache, as we will discuss in a few minutes, if you don't speak with H4 for a while, then you delete it from your cache. Okay? All right, so that cache is called the ARP table. And you can actually type ARP space dash and the letter A. You do that on the command prompt on your computer. Here, I'll show you. I think I got onto the internet today. So let me do CMD. And if I do ARP space dash A, oops, I don't think. ARP dash the letter A. And here, for example, here's my router and here's the MAC address of it. .2, .8, .9. This is all the different type of devices that I communicated with. And they are all dynamic, means that I got it by sending an ARP request. Okay? Let's continue. Oops, let's just go back a little bit. Anyway, so that's the ARP operation. Let's say you have a router right here. So what you first, always by default, your computer will think that destination is inside the LAN. So he'll send out an ARP request. And if the guy is inside, if the person that you're trying to reach is inside the LAN, he's going to respond back with his MAC address, and then you can send out your data. Now, what happens if you went to yahoo.com? You type, let's say, just stay right here for a second. Let's say you type yahoo.com, and well, let's start from the beginning. Let's say this guy is a printer, D is the printer, right? So you went and you said File, Printer, just the word printer, and you hit click and you print, right? What happened is the word printer from the DNS that you have from the DNS server, the word printer gave me 10.10.10.04 address. I brought that address, stamped it on the packet, and now I got his IP address, and I send out an AR request requesting the MAC address of 10.10.04. So I say, hey, whoever has 10.10.04, please give me your MAC. Then D gives me his MAC address, stamp it on the frame, and I send it out. Right? That happens inside the LAN. But what happens if you want to communicate with somebody outside the LAN? You type yahoo.com. So your computer goes out, grabs yahoo.com IP address from a DNS server someplace, and brings it back and gives it to you. So you have the IP address of yahoo.com, puts it on the packet, and now you put that in the frame. You put your source MAC address on the frame, and then your computer thinks that yahoo.com server is local, is inside the LAN. So he'll send out an ARP request requesting the MAC address of that yahoo.com IP address. But nobody's going to respond inside the LAN. Why? Because yahoo.com is not in here. Then by default, you go to your gateway. Right, this guy. You request a MAC address for your gateway. You say, hey, please give me your MAC address because I have a packet that needs to go outside. And then the default gateway will give you his MAC address. You stamp it on the frame, and you send the frame to your gateway. And what does the router do? Pulls the packet out, looks at the destination IP address, re-encapsulates it into another frame, and sends it out, most likely to another router. That is why we need to know, all of us inside the LAN, we need to know who is our default gateway is. Because if we don't, we can never send packets to them. Right? So if you don't have the IP address of your router, which is your gateway, or your gateway is down for some reason, you can only communicate inside your LAN. Okay? Again, by default, you go to the gateway if no one else responds. That's where the word default gateway comes in. All right, so that's what this whole thing is about. I mean, you can go through this step by step, and I just explained it to you and how it works. All right, with the remote communication as well. Okay, so removing entry from the ARP table, that's important. So if this guy, if you haven't communicated with C for a while, usually it's about 7 minutes, then you are erased from the ARP automatically. This is to prevent a lot of attacks, ARP poisoning. You know, somebody might come in here and change the MAC addresses, and you may think it's the MAC address of C, but it's really a MAC address of an attacker. So you got to be able to delete that. Show ARP on the router gives you the ARP and the IP addresses and the MAC addresses that you have sent. ARP-A is the one that I just showed you. Shows all of them. The dynamic one is the one that you requested. The static one means that's part of the, usually MAC addresses that have been given automatically and they're not changed. That's not from the ARP requests. All right. So a lot of security issues, and if you do a lot of ARP requests, that's going to be a lot of traffic. And that's another reason why you want to have smaller and smaller lanes. Okay? So the best thing to do is connect everybody to a switch. And each port on the switch have its own segment. So that's great. And by the way, the carrier sense multiple access is really not needed anymore. I don't think I mentioned that before, but if you have, for example, when you come into a switch, okay, if you're connected to a port on the switch, the port on the switch will look at your destination, find out where you're going, to which port, and it will send you directly. It's like you have your own LAN, your own road to your destination. Imagine that you're trying to go home from wherever you are. And as soon as you get on the highway is like the switch. It looks at where you're going, and they immediately draw a road for you to your destination. You just keep going without stopping. So it doesn't matter if you're going to do CSMA/CD. In other words, it doesn't matter if you're going to go into the entrance of the highway and see if there is traffic or not. There's not going to be anybody in there anyway. So as soon as you go to the highway, keep going, and you'll never stop. All right? But you are born, your Ethernet NIC comes with the protocol, the standard that says you have to go and sense to see if there's traffic, and turn on your collision detection once you start transmitting. But there was never going to be any collisions anyway. This is like your mother always told you, before you cross the road, always look both ways to see if there's traffic, so you don't, a car doesn't hit you. And with today's roads and being connected to a switch, when you go to that road, even though you look both ways, there's never going to be any cars. That road will always be cleared for you to cross. That's what really switches do. Eliminate collisions. It's a collision-free environment, it's called. So you definitely want to connect to a switch. Now, since we are talking about switches, let's talk about the Ethernet switch and how it operates. How does it have the intelligence to find out where you're going and only send that data to that port? Okay? Well, here's how that works. Let me explain. I didn't even have to go through these steps. Let's say you have 3 PCs attached to the switch. You have PC1 attached to port 1, PC2 attached to port 2, and PC3 attached to port 3. Now let's say PC1 wants to send data to PC3, right, for the first time. So he puts his MAC address on there, and he puts, what he does is he sends out an ARP request saying, hey, I don't know where MAC address D is. So what does switch 1 does first? As soon as he receives the frame from PC1, he has MAC address PC1 on it, right? So as a switch, when I look at the frame that's coming, I inspect the source MAC address on the frame, and I know which port he's coming from. So switch 1 now knows that PC1 is located on port 1. Why? Because when I inspect the source MAC address, I see that it says PC1, and he's coming from port 1. So now I know PC1 lives on port 1, and I place that in the MAC address table. In the MAC address table, I'll say that PC1 is located at port 1. So here's another question that you should answer. How does the switch learn the MAC addresses of the devices that are connected to it? How does he populate the routing table? And the answer is the switch inspects the destination MAC address that is stamped on the incoming frame and finds out which port they are coming from. Well, it doesn't even have to find out because he knows he's coming from that specific port. Now, so now I know that PC1 is located at port 1. Now, I don't know where the destination is. As a switch, I don't know where number 3 is. So if I don't know where the destination is, what does the switch do with a frame when he does not know where the destination MAC address is located, which port? He floods the ports, which means he sends the frame to every port on the switch. And when he does that, PC3 then sends back and responds back, and when he responds back immediately, of course, S1 will say, aha, now I know where PC3 is located. He's located at port 3. And eventually he'll know where PC2 is. Once he learns where all the MAC addresses of these 3 PCs and which ports they are located at, so now every time you send me a frame, I'll just look up my MAC address table, find out where that MAC address is, which port they're located at, and I will send that frame to that device. All right, that's called filtering. Those MAC addresses, again, in the MAC address table are aged. So after a certain amount of time, if you do not communicate with the switch, you are erased from the MAC address table. Another thing you need to remember, if you never send anything to the switch, in other words, if you connect the PC to the switch and the switch never sends anything, the PC never sends anything to the switch, the switch will never know where you are, right? So you have to send something to it. We'll do that, by the way, next semester when we talk about security, and when we want to tell the switch, for example, listen, I only want MAC address PC1 to be located in here. So he has to send the ping command to the switch to identify himself, so he can learn. Otherwise, you have to go to the switch and type the MAC address. We'll talk about that next semester. All right, let's talk about duplex settings. I think we discussed that also in chapter 4. Half duplex means that I can only send or receive at a, send or receive. You can't do both of those at the same time. If you're connected to a hub, you're going to have CSMA/3D. That means you can only send or receive at the same time. Nobody uses hubs anymore. With switches, you can do what's called full duplex. That means you can send and receive at the same time, right? So I could be printing and receiving data from the file server at the same time. So that really doubles my bandwidth. Okay, so full duplex Ethernets are great. They're a little bit more expensive, but that's the preferable way to go. Okay, all right. By the way, also the switch will negotiate that with the PC. Some NICs may still be half duplex. So what the switch says, hey, are you half or full? If you say half, then the port on the switch will become a half duplex to allow you to either just, send or receive. And if you are full, the switch port will switch himself to full duplex. Okay. Now, they're switching auto MDIX. MDIX is a feature on most switches today, and what they do in case, remember we talked about cabling, and when you put two cables next to each other, if you have similar devices such as switch to switch, you should have a crossover cable, not a straight through. But with MDIX feature on the switches, what they do, you can have a straight through. What the MDIX feature does is it looks at the port, sees that you are a straight through, and he will adjust, configure himself accordingly to make sure that you can communicate with the straight through cable. So really, if you screwed up and you put a straight through instead of crossover, MDIX will take care of that. So that's nice. Some routers do have that feature on that part of the NIC, and some don't. If you are using packet tracer doesn't do that stuff. You got to have a crossover when you're connecting something like this. But in real life, if you're using the 2960s, a lot of them do MDIX. All right, forwarding method. There's two types of forwarding method switches to use. There's something called store and forward, and another one called cut through, which we'll discuss in a minute. Store and forward method means that when you send out a frame, the frame is stored inside the switch, and I calculate the FCS number, check to make sure that the frame is good, and if it's good, you send it on its way. If the frame is bad, you drop it right here before you send it to its destination. That's called store and forward. Now, that creates some latency, some delay, but it does error checking. You're not sending any bad frames to the destination. And the idea, if you send a lot of bad frames to the destination is ultimately going to ask you to retransmit, and that creates more traffic. So in a very busy environment, store and forward switches are good, but they're a little bit slow. On the other hand, cut-through switches means you want to speed things up a little bit. There are two different types of cut-through. The first one is when you come in, I just look at your destination address and you zoom right out. I don't care if you're good or bad. That's not my problem as a fast forward cut-through switch. But that offers the fastest connection. There are some cut-through switches, what they do, they say, hey, listen, I'm going to look at the size of the frame. If you are less than 64 bytes, sorry, you're not going, because you're bad. You're a bad frame. Why even bother doing that? All right? So that does not mean if you're larger than, if you are bigger than 64 bytes, you are good. But fragment-free switches, at least they eliminate a lot of bad frames. If you are less than 64 bytes, you are definitely good. And a lot of, if you're in a collision environment, 64, when you collide with somebody, most likely you're going to be less than 64 bytes, so you get dropped right here. So fragment-free offers some error checking, but not, completely, not as good as the, I should say, the store and forward. All right, now, inside the switch, there's two different types of memory to allow you to communicate. For example, if the server is 1,000 megabits per second and you are only running 100, if the server starts sending you data at 1,000 megabits and you are 100 base T guy, that's 10 times faster than what you can process. You gotta tell, hey, slow down a little bit. What usually happens is you are assigned port-based memory switches. You are assigned a memory space inside the switch. So that server, instead of sending you the data directly to you at 1,000 megabits per second, they send it to your memory location. And you go into your memory and you grab that data at your leisure. The only problem with that, what happens if that space that is reserved for you gets filled up? That means the server has to slow down and wait till you unload. Right? This is called port-based memory, so it's not as efficient. The shared memory says, all right, we're not going to reserve memory location for each port because a lot of the other ports are not even going to be using it. They may not be using their ports. So why don't we just use the whole memory? So if somebody wants to communicate, if let's say I want to communicate with the file server and I'm the only one that is connected to the file server, then the file server will send the data to all the memory, to the whole memory on the switch. And so therefore you can send it and the whole memory will be for me. Now if someone else comes in and wants to communicate, then the switch will immediately split the memory between us. We share the memory. So shared memory buffering is a lot more efficient. All today's switches use shared memory with fragment-free. Actually, they're called also adaptive. They're either adaptive switches, they go store and forward fragment-free, store and forward fragment-free, back and forth, depending on the traffic. But they also use shared memory buffering. So today's switches are adaptive. Adaptive means they go between fragment-free and store and forward, and shared memory buffering. So another question, what are the two different type of memory bufferings that are used on the switches? Port-based and shared memory. All right. Also, switches can come with the feature called PoE, Power over Ethernet. If you want to connect a voice over IP phone onto your switch, the switch can provide, using one of the cables on one of those 8 wires in the Ethernet patch cable to power your phone. So your phone doesn't have to be next to an outlet. All right, but you have to purchase that feature. And here are the different types of switches that are out there. There are the fixed configuration, which means if you get 24 ports, that's it, you cannot expand it. There is the stackable ones where you can add more ports by connecting, daisy chain the switches on the back. Not a lot of people use that. But there's the modular ones where you can just buy the chassis, buy the big module, and every time you need more ports, you just buy them and slide them in there. That's a little bit more expensive. Here are more options for the switching slots, the SFP modules. Here's the optical gigabit Ethernet connectors that they have. Remember, fiber optic Ethernets are always full duplex. It's never ever half duplex. There's always one wire for sending and one wire for receiving. All right, now let's discuss the layer 2 switches. What is the difference between layer 2 switch, layer 3 switch, and the router? Well, let's talk about layer 2 switches like here. A layer 2 switch is a device that only works with frames, and frames are layer 2 data. So he takes a look at the MAC address that's stamped on the frame and trying to find where the destination is. If your frame is trying to go to in a different LAN, because remember that MAC address that's stamped on the frame only identifies a person, a name of a person inside the LAN. You have to be in that LAN, otherwise the layer 2 switch doesn't know what to do with you. Now, if you need to communicate with somebody in another LAN, that's why you send your data to a router. Then the router pulls the packet out of that frame, and what's on the packet? The IP address that identifies which LAN you are in. And then the router will re-encapsulate that packet into another frame and send you to that other LAN. That's what a router does. So a router is considered to be a layer 3 device. But the problem with, well, not a problem, but the router to do that, let's say you are in a building and you're trying to send data, you're a student and you want to send your frame to a faculty member, and he is in a different LAN. So you send it to a router, the router will do the job for you. But to have a router pass data from one LAN to another LAN inside the building is really a little bit of an overkill, because the router is really designed to route packets, to find the best path to a destination, connecting big LANs together to the outside world. They run advanced routing protocols. You can run security. They have many, many different features, so they're a little bit more expensive. They're not really designed, although they can, they're not really designed to connect local LANs together inside a building. If you just want that, what they do is you take a layer 2 switch, you give it the intelligence to pull a packet out and re-encapsulating it into another frame and send it to another LAN. Now, if a switch can do that, can get into the layer 3 packet, pull it out and re-encapsulating it into another frame so he can send it into another LAN within the same building, and it's called a layer 3 switch because he's able to access the layer 3 packet that's inside that frame. But layer 3 switches don't do what routers do. They don't run advanced routing protocols like OSPF, EIGRP, or RIP2. They run hatch serial ports, for example. So it's a lower than low-end routers. Okay? So this is typically what is found inside a corporate environment when you want to connect inter-VLAN routing, it's called. All right, so we'll discuss a little bit about that later on. All right, so the CEF is the software that runs on those layer 3 switches to enable you to do that. All right, and the difference is, we'll discuss when you type INT, there are 3 different layers. INT VLAN 1, for example. Give the VLAN 1 an IP address. Layer 2 switches allow you to do this SVI, so you'll be, and even layer 3 allow you to do that too, to enable you to telnet into the switch so you can manage it. But layer 3 also allows you to do what's called a router port. If you type the command, let's say you type interface fast Ethernet 06 and you say no switch port on it, then you can assign it an IP address and it will act like an interface on the router, like a default gateway. If you type no switch port on that interface of the switch, you cannot type no switch port on a layer 2 switch. It will, if you try that, it'll tell you, unrecognizable command. And we'll discuss also the Ethernet channel, where you can bundle a whole bunch of ports together to give you, aggregate the ports to give you bigger bandwidth. So if you have ports that are not being used, why not use them, right? As a trunk to give you higher bandwidth. We'll discuss that next semester, the Ethernet channel. But layer 3 switches allow you to do any of those. Okay? So here's typically 0. If you go to an interface on the switch, you type 0 FA, interface FA 06. You type no switch port, then that port becomes like a NIC. And you can assign it an IP address, a NIC on a router, like a default gateway. And when you type show IP interface brief, you can actually see it with the IP address. You cannot really do this on a layer 2 switch. You can only do that on layer 3. All right, and takes us to the end of chapter 5. Next week, next chapter, we'll be talking about the network layer. We'll see how and then we'll get into subnetting later on. All right. I'll show you an easy way to subnet later. So please answer the questions that I talked about and submit them as homework. And if you have any questions, by the way, please ask. Always ask. So this way, if you have any problems, we can discuss those. Bring those. I'd rather you bring it to class than email me. But if you don't understand anything, just send me an email or bring up the question in class. All right. So we go over it. I want to make sure you understand everything. And don't forget, you should definitely read the book. Reading, listening to the lecture does not exempt you from reading the book. You still need to read the book. All right? Alrighty, guys. Until next time, God bless, and I'll see you in chapter 6. Take care.